the end of the video. Worst comes to worst, I record period 6. So yesterday we saw that the definite integral is the actual area. So if you guys need to tie those two together, you totally can. That the definite integral itself is the actual area between a function and the horizontal axis. It can sometimes be positive, can sometimes be negative. We haven't seen negative yet. But if you guys think about how there's motion that can be in the positive direction and the negative direction, it might make sense that there can be a change in position to the right or to the left that would be positive or negative. So we'll talk about that a little bit more as we go on. But the AP more and more, starting a couple years ago, is including these concept-y questions that don't necessarily make you solve for the actual area, don't make you solve for the definite integral using this definition. Now with derivatives, of course, they do. With derivatives, they can give you something nasty where it forces you to use the definition. Like if you saw something on an AP exam, and I think we even saw one on the sample one after Christmas break, that looks something like this, sine of, make it a little bit, plus h minus sine of pi over 6 over h. Now, we do kind of need to rework our L'Hopital's rule and those sorts of things, but this doesn't need L'Hopital's rule. I've been talking with BC about how we've figured out how the AP guys perfectly want us to show our work for limits in the free response. And so we'll get to that when we get to AP practice. But for right now, this doesn't need L'Hopital's. You might think it needs L'Hopital's because if you plug in 0, isn't that going to be 0 over 0? But it doesn't need L'Hopital. Because what does the derivative definition. This is f prime of x. But we have to figure out who is to do this. We don't have to solve that limit. You kind of could with L'Hopital's if you could figure out the h instead of the x, and it's kind of confusing. So it's a whole lot easier to think of who is your f of x. And actually, it's not even you guys know we're going to change the x. And not h. Good idea. H is a part of the definition. Pi over 6. Because it's f prime of a. Remember x and f prime of a? So f prime of pi over 6, f prime of a. But I need to figure out, okay, who is my f of x to do this? And, okay, well, technically, we already figured out that a is pi over 6. So who is your f of x? What is the function that plus h and a, or pi over 6 plus h and pi over 6 are being plugged into? Up there. Who's the outside? Sine. So without doing a limit, we just say, oh, hey, that's the limit definition of the derivative of sine of x at pi over 6. So how do we solve it? We say, forget the limit. I don't like the limit. I can do the sine. The derivative of sine is cosine. And hopefully, so cosine of pi over 6 would end up equaling, it's all right, I'm spotting you, square root of 3 over 2. Square root of 3 over 2. So then, coming on over, there are problems that require us to use the limit definition of a derivative, because without knowing the definition, we're stuck. But there are not going to be problems that make us solve with the limit definition of an integral. But what they will ask is what you guys, if you did peek on homework and work on your 50% of it, that make you use the idea like this. The direction said express or show this quantity as a definite integral. Now, in homework, those of you guys that tried it, were there ways of figuring out who A and who B were? Yeah? Okay. So with homework, there were ways of figuring out who A and who B were. But if you're just looking at this limit definition with no extra, like, oh, between x from 0 to 2, you wouldn't know what to make the bounds. And so I went ahead and put bounds because this is talking about a finite area, but we just don't know what the beginning and end is without a picture showing us the left and right of the area, the shaded region, or without showing us x equals a to x equals b, x equals a to x equals b, and some sort of interval. So that's why I just put a to b, but then all I needed to do to write it as a definite integral was just realize that your little c's, we'll just look at the definition, your little c's are actually x's. So the little c sub i's, that could be like for each subinterval, the left one, that's what got plugged in as a c's, or for the little subintervals, a right hand, the right one, or the little midpoint got plugged in. Or if the AP were to give you other c's, you're like, okay, whatever, give me whatever you want, and I'll use them. So the c's were just the x's, so all you have to do is replace the c sub i's with x's, so 6x times 4 minus x squared. And then your delta x, which was your little bases, we just get to make the dx. And once we learn how to solve the definite integral, we could go from there. Now, what we didn't get to do was actually look at some graphs. So what if they were to give us graphs instead, which theoretically, hopefully, some of you guys saw in homework who were able to attempt. But if you have these shaded regions, and in homework they should have been shaded as well. There we go. Now we can know the bounds because we can see the actual shading. Now we can know the bounds because we can see the actual shading. Yeah, I'm just going to put you in the back. Is that okay? Do you have a phone on you? Yeah, just put it upside down on my stool. And you can grab it on your way out, okay? Thanks, bud. Good luck. Have fun. All right. So we know it's going to be a definite integral. What would you guys say are your bounds for this first one, for letter A? Yeah, because you have to use the x values. Just a few people might accidentally use 0 to 4. So 0 to 2 are your x values. Now I need an integrand, right? And so where am I going to steal that from? Yeah, just the function. So 4 minus 2x. Now pause. If there's ever an addition or subtraction, you need to put parentheses in. I know it's kind of annoying, but it's your way of showing this is the entire integrand. If it's like a monomial, it's no stress because it's naturally grouped together with order of operations. But if it's an addition, a subtraction, we need to go ahead and make sure there are parentheses in there because what's still needing to come? I know it stinks. But on like free response questions where they're not saying write an integral expression, that's not even the point. It's just a part of the problem. If you were to write this without the dx, and even the BC kids do this, they just get lazy. If you were to write this without the dx, the AP guys are going to have to say, that's incorrect notation, I have to take off a point. And I know that seems silly to you, like, come on, they knew what I meant. But in their minds, the free response when they're grading it, it has to be seamless. It has to be perfect. There can't be a hole. And if you've ever listened to a debate, wasn't there like a very interesting debate club this week? If you're ever listening to, if you're ever listening to a debate, even like, right? Someone can sound amazing, and especially in like mathematical proofs, a bit more personal. Or in a scientific, my sister teaches, well, she's on sabbatical this semester, but she teaches university, cell molecular biology, and she tells her kids it has to be perfect. In a biology class, when they're trying to explain, I don't know if it's lab procedures, no, it was something in lecture. Anyway, I don't understand because she went science and I was like, and I went math. But either way, she had better science teachers too. You guys have amazing science teachers coming back. Math teachers. When you are explaining something, when you are, dissertations, that's or building an argument, proof for something. Someone can point to a hole in your argument. What does that do to all of the rest of it, even though it sounds great? Yeah. Yeah. And you guys know with politicians, I know it's kind of like a celebrity game too, and who has the most money. We're trying to not do that for the next election, from what I can tell from the different candidates being like, we don't want the big money. Coming back. If you're looking at candidates well, and if someone says something foolish, who cares everything else? A good candidate. Like, I don't trust you. If a friend says something and then all of a sudden you hear something behind your back and you're like, I don't know if I trust you, right? That's kind of, I know it seems silly, but that's kind of what the AP guys have to do, being like, oh, I'm going to give you points, and they're really nice. We're going to give you partial credit, but if we see an error, if we see an argument, if we see a hole, we can't give you full credit. Does that kind of make sense? So it's not just them trying to be mean. It's them trying to be like, no, it has to be precise. And in any field you are, it has to be precise. Well, off sciences and humanities. And anyway, coming back. In the STEM, it has to be precise. So what would you guys say with this one? Okay. I'm going to be mean because I just said you always use the x's when you have a dx. I know, it's so mean. So why is it 0 to 4? Why is it not 0 to 4? Sorry. Because we're going to write this. Ooh, there's another one. Yeah, you got it. Always, they only use the x's. No. So you found a hole in my explanation, right? Because you were like 0 to 4. She just said, always use the x's. What should I have said? Always use the x's when in terms of x. Does that sound better? So now we're going to use the y because now we're in terms of y's. Ooh. Now don't just stop trusting me. I was proving a point, and I should have said it better, so it is my mistake. But I promise, for the most part, I know calculus. Okay, so coming back, because I just totally was an argument for why you should stop listening to me. Stop. No, listen to me. Okay, but now we know. You always use the variables that the integral is in terms of. So if your integral is in terms of x, use x's. If your integral is in terms of y's, use y's. If your integral is in terms of thetas, use thetas. Because not only do we have a function of y with a dy, but these need to be y bounds. Because if you have a function of y with dy and x bounds, illegal. Okay. Moving on. Did anybody get stuck with the a's last night? Was this a problem at home? What? Go team. What do we do when they give us constants? Ooh, where else have they given us constants this year? Choose C, choose K. Have so much fun. They're going to universal. I'm jealous, but it's cold, so maybe I'm not. And there's the stairs. Well, last time I was there, why did we get a free pass? Free, like, front of the... I mean, like 3 times. It's like, good ride. Coming back. Didn't earlier this year, wasn't there a problem that said choose C or choose K to make F continuous with a piecewise function? Or choose A and B to make it continuous? They love putting in A's and B's and K's and C's and making you find them. So don't get tricked by the little random constants. I don't know how to say it nicely. Ryan, think of it. Okay, so how can they expect us to solve that? Hold on, we saw this yesterday. What happens if we have a 4 inside? What kind of graph is that? What kind of function? Good. Good, good, good. Okay. Something that was so hard in Algebra 1. Anybody else struggle with that? Y equals X equals which way is which? Hopefully we have it now. So we have Y equals 4. How do we find the area? Well, wait. We talked about this yesterday. Isn't the area just a rectangle? And aren't rectangles just bases and heights? Wait. But how left and how right? Kind of, right? We just have negative A and A, whatever it is. It's kind of arbitrary, except there is a pattern. And the pattern is, whatever negative A and A is, how are we going to find the area? My height's going to be 4. That's for sure, no matter what. And my base is going to be, don't think that you need to find a number. You don't. You need to find an expression. So, what? Yeah, and what's A minus negative A? A, 2A. Final answer? It wasn't a number. It's an expression. When they say expression, it can be equals. Oh, all right. Got it? So in your groups, ready, set? I'll give you a hint. It is him. But he's been, and he's been. Go. Draw a picture. Try to figure out what the formula would be for the area of B. If you figured it out last night. Ryan, scooch over. Go with David and Janelle, or with Alec and Thomas. Go over in that direction. Oh. He's trying to do it in a, there you go, there you go. All right, draw a picture. I would start there. It's a V, but he's been whoosh, he's been whoosh. Triangle. Good. And you can label that, right?
It's what you drew. The height is 8.
Oh, yeah. And then the height.
And so it's called 2A. 2A squares and 1/2. The base and the height should be. And the height is. Okay, the base is 2 times the height. Yeah.
Some of you guys have figured out the picture by now. Some of you haven't. The picture's now up. Pretend it's perfect. Sorry, it's not. Life is beautiful because of imperfections.
Base times height? Wow. My intelligence goes to a certain point, and then I start talking about it.
Did you guys get the 2 and the A? But don't forget your 1/2 base times height. So A squared. We got it? Go team. High fives all around. Who got stuck on this in some way, shape, or form last night? Ah, but now does it make sense? Ah, go team. Motion packet. Ooh. Ooh, motion packet. Oh, motion packet. Oh, they gave that disclaimer that day. I was like, oh, I'm not trying to make you feel bad. I'm sorry. You're good. You're good. You're good.
Buying a car, Thomas. How do you buy a car? This is what.
Wasn't that like over a week or something? Oh.
They also had a product.
But to be honest, financially, there are many things to consider when buying a car. If you can pay cash up front, it's you're going to save a whole lot of money versus payments over economics in another way. I don't know if Mr. Jones' advice lines up with personal finance and financial peace. Anyway, so it's the one in horrible investment, unless your car is going to become a classic. Or these days, unless it's a truck or an SUV. Those maintain their value pretty well, for the most part. Yeah. Yeah, trucks and SUVs hang on to it. Like as soon as you drive it off the lot, like, lost money. All right, here we go. But he is true. You should always barter with a car salesman. Not that I've ever bought a new car. All right. Number 4. Good try, trying to get me off on a tangent. Calculus. Anytime someone says it, like, do you really know what that means? Like pastors say it a lot, and I'm like, did you take that? I don't think you did. Anyway, but they could have taken geometry, going off on a tangent. All right. Speed is the absolute value of velocity. We knew that. Hey, it's like a sum up of what we already know, right? If the velocity and acceleration have the same sign, increasing. And then when is speed decreasing? Don't you guys love these kinds of questions where you just have to look at the one below to fill in the blank above? But opposite? Nice. Okay, keep going. We already knew all that. Whoo, but now what? Oh, Okay, all right, here we go. What's the difference between this guy and that guy? Because there's two different questions. We're problem solvers. One's indefinite, the one without bounds. This one is going to have antiderivatives plus c. Ooh, we'll get to that in a second. And this one is definite because it has, wait a minute, why on earth are the bounds little t's? Right, if we have dt and a function of t, then it's going to be times. But time is usually on the x-axis, so it's kind of the same as far as looking at a graph. Up here. What will the integral of velocity be an expression for? Careful. Yeah, does that make sense? Going back one. Good, good, good. Position at time t. Don't forget that you will have a, because it's indefinite. We're going to have an antiderivative. If you want, you can put an antiderivative in there too. That's all you got to do. Antiderive and you're done. Antiderivative, if you want to put a plus c. Okay. But in number 5, you have bounds. Put it in your calculator. What is it going to spit out? An equation? What's it going to spit out? A number. Yeah, a constant. Unless you have something like the a's, and then you're going to have like an expression. But that was them being tricky. Look at that. The number represents the change in position. It's still going back to position. But do you see the difference? This one gives you a position expression like x of t plus c, if you want to keep going with that. It's going to give you an equation for position. This one's going to give you a change in position. Ooh, like displacement, like final position minus initial position. By the fundamental theorem of calculus, since v of t is equal to x prime of t, the integral will yield, by the fundamental theorem of calculus. Guys, what's section 4.4 called? We haven't covered it yet. It's all going to come together. So we're going to learn why the definite integral is going to become, but it is going to become, and remember the whole peek behind the curtain I explained Wizard of Oz yesterday? I already showed you how you anti-derive and plug in the top minus plug in the bottom. But maybe you haven't exactly fully gotten that one in yet. This is also known as, hey, it's right there, displacement. The answer can be positive or? It's having too much fun back there. Depending upon if the particle lands to the right or the left. And that was kind of what I was talking about earlier with the positive velocity, negative velocity. It makes sense that even though you would say, how far away are you? And you wouldn't tell someone a positive, negative distance. If you're thinking about direction, well, technically you could one direction or to the other direction. So we would say positive or negative with changes in position sometimes. But how about number 6? Also a what? Definite integral because it has bounds. So the answer will be a number. Okay, fine. They like number better than constant. Should have gone with Nick. But either way, it's a number, it's a constant. Is also a definite integral. They probably like number better because constant is like, it's always the same. Well, no, change the bounds, it'll be different. Anyway. I have T somewhere. The number represents the, yeah, but not just distance. You're right. I'm going to add a word. I know it's only one blank. I know. Total distance. Is there a difference between displacement and total difference? Total distance. Yes. Total distance will always be positive, which kind of makes sense because speed takes all the negative values of velocity and say, I don't care what direction, I just care how far. I'm going to ask you guys a question real fast. It's going to not take us long. What if the podium is position 0? Okay? Now, I could start somewhere away from the podium. My initial position would be 3 units of something. How tall is 3 feet? Half of me. Anyway, so I'm 3 away, right? 3 in a positive direction. What if you were to start the timer, right? Now I was to walk over here. And then I was to kind of walk, well, I have to keep it in a straight line because that's the kind of motion that we're doing. It gets hard if I go over there. And then I walk over here some more. And then I walk over here. Oh, and I go back to the beginning. What was my displacement? 0. I end versus where I began. I began where I ended, exactly. Does that make sense? So it's a position was my position 3 again. Let's pretend I'm in the same spot. I might be a little bit off. Okay. 5. My total distance. Oh, yeah, I mean, something, right? Sure, sounds good. You see, start measuring, and it was maybe like 4-ish that way, and then it came this way, and then it came that way, and I was like, okay, more. Total distance traveled, like your odometer. Do you guys know the parts of your car? What's the odometer? Some people meter, tripometer, however you want to call it. It's the mileage, how far you've gone. Does it like subtract things when you go backwards? Oh, the old cars. Anyway, there were movies that you'd put the car on, and then you like run it in reverse, and then you would count down the odometer. Anyway, so, but no, it just adds. It just adds. It just adds. It doesn't care which way you're going. It just adds, which is my mileage is almost 300,000 miles. Anyway, but coming back, it just yeah, it's an old car. It just adds. He's running great. It's a Toyota. It just adds. Saving money. Okay. It was an aunt's car, so just pass it down. They had money. They kept it up at night. It's a grandma car, really. Coming back. My dog likes it. He doesn't slip on the seats because it's like carpeted. But then coming back. Total distance adds. But this one, since velocities are positive and negative, positives and negatives take away from each other, detract from each other, which it should for displacement, because my displacement was 0. Don't worry, I'll spray some Lysol. But total distance, I need all of the changes to be positive so they can accumulate. Ooh, accumulation. Good calculus word. So, forever card in your notes. To end section 4.3, mostly. I want us to add in, and it's basically because of our motion packet, but it's important to calculus. It might show up in homework at some point. It will, especially in AP practice. Total distance traveled versus displacement. Total distance traveled versus displacement. Total distance traveled is easy if you're able to use your calculator. It's do it by hand. Displacement is easy if you have position, because it's just x of t2 minus x of t1. That's a very mathematical way of saying it. Physics people would say, like x sub f minus x sub 0, x sub I, final minus initial. We could even talk about like a time interval a to b and x of a. Oh my goodness, that's the building of average velocity, change in position over change in time. Displacement is just a change in position. Positive and negative, in a sense, against each other. The definite integral from t1 to t2 of velocity. Full distance traveled, and I need speed. I need all those velocities to be positive so I can just add up all those changes. Once again, super easy if you have a calculator. You can just plug it in. Sometimes they let you do that because they're like, well, you have to have the right integral in your head or else you'll get it wrong. So it could be a calculator question, but if you have to do it by hand, we're going to have to learn how to do that in a couple sections. This is forever number 31, yeah? Oh, bummer. I was so close. Too many forevers. Oh, yeah, because 30 was the beginning, then we had 31, and now oh, yeah, too many forevers this section, huh? Technically, this brings us back to the very first page of your motion packet, the number that we skipped. Can you go look at number 11 on the very first page? What was that question that we skipped? Fine. Might not be the exact wording, but the idea is there. Find the total distance traveled, and they gave us position. Ugh. If you're trying to do you see how I wrote something with position for displacement and I didn't write something for position with total distance traveled? Because the long story short, I don't like going from position to total distance traveled. Because we have to go find all of our resting points. Think about my travel over here for number 11 if you're looking at it. What changed when I was backtracking on my distance traveled. Does that make sense? For displacement, I had to backtrack some to end up at the same spot, right? So what was happening when I was changing? I was changing direction, so I like went a distance, but then displacement, I was backtracking, so then I kind of made all of that null and void. Then I went over here, then I changed direction, right? What happened in between me changing direction? What always happens in between changing direction? Change of sign. What happens, intermediate value theorem, always between a negative and a positive or a positive and a negative? A zero. So how could we do total distance? Well, what we have to do is say, well, how many times did the something or other stop? And then we have to figure out, okay, well, how far did it go before it stopped? If it's negative, make it positive. If it's positive, keep it the same. How far did it go after it stopped, in between that and the next stop? If it's a positive, keep it the same. If it's a negative, change it. You'd have to go through those little displacements, absolute value of displacements, in between every single stopping point, because who knows? And maybe, the stinky little particle is just like, I'm going to stop just because I want to stop, and I'm going to keep on going. So that might not have even really, I still don't know unless you model every piece of that journey in between each stopping point. That's how you would do number 11. Maybe someday we'll get there, but for right now, I want us to at least introduce section 4.4. Don't worry, motion packet's not homework, it's not due on Monday. Motion is something I'm just going to keep reminding you of because I want you to be relating integrals with motion. But do you remember that day when I was like, why is motion important? And I had you go back to the very beginning preview of calculus. Remember that day? And what did you say, or what did you find when I first described calculus to you? Not like as a class and not like the coursework and all the syllabus day, but the preview of calculus. Calculus is the math of So is motion only feet, meters, seconds, hours? No. Remember what I said also moves? Stocks, prices, water going in and out of a tank, people flowing in and out of an amusement park, temperature of biscuits just being pulled from the oven. Yes, that was an FRQ once. Biscuits and tea. The biscuits being pulled out of the oven and how their temperature was falling to room temperature. Motion. There's motion everywhere. So even though that packet deals specifically with like physicsy, oh, hey, look, I'm watching a car go by, or I'm watching a particle go back and forth. All of calculus is motion. Any stinking word problem, any scenario, any story they can throw at you, if it has to do with biscuits and tea or gravel or bananas, oh, that was a year. A store opens, there's no worker restocking the bananas. Customers start taking the bananas at a certain rate. Oh, the worker comes on shift and starts putting the bananas back. Motion. Kids didn't like that problem that year. But it was still just motion. Anyway, so that motion packet's good, but I don't want you to get stuck in only that kind of motion, but I do want to always be reminding you that calculus has to do with motion. Section 4.4, fundamental theorem of calculus. What have we done so far? Do you guys see that I just kind of keep building? Didn't we write down key ideas for section 4.3? Am I just reminding you of stuff? Yes. Graphically, hey, there's a curve, and hey, there's... Look. Solved with geometry. Oh, I don't mind this type of problem if it's just sort of geometric shape and add to it like an upside down. These kinds, something like one height. Will every single area be geometric? No. So then we started talking about if you have a thing, say to approximate said area in between A and B. And they give us something, let's split this into fourths. And you're like, okay, fine, I'll split it into fourths. I'm going to hit at the left, maybe. Or I'm going to hit at the right, maybe. Or I'm going to hit at the middle. Or I'm going to make trapezoid. Goodness, so many options. What do they tell us? They're making the answer key that score our exam. With motion. Now we've talked about How to go backwards from acceleration to velocity. How to go back from velocity to position. Then we also just talked about what the definite integral between A to B represents as far as displacement. You're welcome. Versus the integral from A to B of speed, total distance traveled. But algebraically, how do we not use a graph? How do we not use rectangles? How do we not just use our calculator? That's what section 4.4 seeks to answer. Section 4.1 was all about indefinite integrals, antiderivatives, even with position. Sometimes we were plugging in stuff, but even then, indefinite integrals. Section 4.2, area approximated with rectangles. Section 4.3, there's a definite integral and it ties together with the area. Section 4.4, how do we do these puppies by hand? You guys got it? Sorry. We're okay? Ish? Okay. Let me zoom in. I don't know why it's so zoomed out. Using the idea of area. Using the idea of area. Before we get into how to keep going with an integral, let's at least say or talk about how to read an integral and see if there's anything right away, even before solving by hand, that we can figure out. Problem number 33. Before even solving an integral, before needing to keep going, just looking at it, there are a few things that you can tell. First of all, this was a sweatshirt a few years ago. I used to have one. I don't think I have one now. Do I have a t-shirt of it? I might. On the back of theirs, they put hours of sleep a CalcAB student gets. And they did A to A of f of x dx. And they're like, bah, ha, 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 ha. Because it was 0. But why would it be 0? Yeah, if you're at A, going to A, have you gone anywhere? No. And it's one line. Does one line have area? No, it has no depth. It has no width. It only has length, and width is 0. Which is why every time we draw a line on a piece of paper, and technically it's like, that's not really a little bit of space, but oh well. But yeah, A to A, you didn't go anywhere. There's 0 area. So anytime you have an A to A, whether it's 5 to 5, 3 to 3, 1 to 1, 0 to 0, doesn't matter. Always 0. Boom, done. Number 2, what do you think I mean by writing B to A, B on bottom, A to top? How is that going to look? How have you been writing all of your definite integrals up to this point? A to B, and this was what type of number compared to that number? Lower or higher? Lower to higher, beginning to end. What if they switch the order on you? What if on a graph you're not going left to right? What if you're doing it in Hebrew? You're going from right to left. It's okay. We can still do it. We have to think, if you're ever moving backwards on a graph, opposite going forwards. Should kind of make sense somewhere up there without me explaining it too much. But if it's 5 to 0 or 2 to 0 or 3 to -1, if it ever gets flipped, and there are times and purposes when we would do that, going backwards, well, it's opposite negative going forwards. We've already kind of talked about with sigmas how if there's a constant, it's been distributed to everything, so we can just pull it out of everything. If an integral is really adding infinitesimally small rectangles, we can take that k out of everybody and just deal with the inside. If we're going from A to B, like from 0 to 5, we can go from 0 to 2 and 2 to 5. But what's also weird is we can go from 0 to 7 and 7 to 5. We can go too far and then backtrack, subtract, and that also works. But at beginning to an ending, we can always go to an in-between point. That's a good property. Then last but not least, we can split up addition and subtraction. What does all of this lead us up to? Okay, fine, but what do you do next? And you've seen it, you've seen me do it. The question is why? But we're not going to get to that today. That's going to be on Monday. That's going to be our finishing 4.4, seeing not just the subtraction of the antiderivatives that you actually kind of wrote out on your motion packet today, x of t2 minus x of t1 is the definite integral to be a velocity. But I'll blow your minds on Monday with the why. But how could you still start homework 4.4, not just finish up 4.3 this weekend? Because what if they don't make you solve it? What if they give you little baby, nah, I'm going to draw this in blue because what? Clues. Okay, we're trying. How on earth could you do something like this? Be like, oh, the bounds match, so I can do something like 3 times the integral 1 to 4 of f of x dx, which I have a clue for, minus the integral, oh no, it's already bad. Clue for. Bye, guys. See you later. Happy weekend.